there any questions?
How many degrees do you want, sorry, how many decimal places do you want our radians to go out to for this? 4?
4 sounds good.
She was like, you want to write the W?
All right, so we've done some of the vocabulary already. I feel like we've already talked about wavelength, period, frequency, amplitude. Yeah, we can. Okay. You started nodding with confidence, and then the facial expression said, I'm not 100% sure.
We have.
We have,
It's just
okay.
wavelength threw me off. Wavelength.
And the symbol for wavelength?
It's a W. No, it's a Y.
A lambda?
Then I made it up.
Thank you. Lambda.
Yeah.
Frequency?
Lowercase f.
Period?
T.
More specifically?
Capital T.
All right. And what is the relationship between them?
Between frequency and T.
Any of them.
Frequency is the inverse of T, the period. And, sorry, lambda is,
Wavelength?
Sorry.
Lambda? What do you call it?
wavelength is the distance between, that the wave travels between one period.
All right.
Are you looking for like a value or something?
And then we have that, just looking for the basic equations right there. Have we done transverse versus longitudinal?
No?
All right, so let's begin there. There are two basic types of waves, transverse and longitudinal. Some sources will supply, two types of mechanical waves, as opposed to electromagnetic waves, which is next semester.
What's a mechanical wave?
Mechanical wave is a wave that requires a medium. It requires particles to move in order for the wave to.
Basically anything but radiation.
Yeah, pretty much.
Requires substance to move.
Especially in classical physics. So mechanical waves. There is a third type that some textbooks will use and some will not, and I'm just going to put it in parenthetically, surface.
Oh, like surface tension?
Surface wave that if you look at water as it is moving, it's just, there's the wave traveling over the surface.
Okay, so that's it.
The reason why I put it in parentheses is that, well, we'll get to it. All right, transverse waves. The particles in the wave move perpendicular to the wave. So if I have a long coil, or if I talk about battle ropes, the exercise, we got one person who understands, got two, just two of you.
The what?
Battle ropes? Yeah, that's the one. When you are using a battle rope, so it's for those who don't understand, it's a rope that is tied to some fixture, I think on the wall.
CrossFit stuff.
Yeah, it's an exercise thing, and you basically do this with the ropes. And then presumably better stance and posture and breathing and all that other stuff. But you have a long rope and you go up and down on it and a wave goes propagating through it. The wave that is propagating through it is a transverse wave. Because the particles in the rope are just moving up and down, but the wave is moving sideways. Let's see how well I can do this without destroying anything. transverse wave because the coils themselves were moving up and down, but the wave moved out, hit the boundary, and came back. We'll demonstrate that better in a moment. Longitudinal waves, well, if it's not perpendicular,
It's parallel.
yeah, the particles will move parallel to the wave. And the slinky. Just missing it? Anyone see the slinky? Is it on the ground? Dang it. There were two in here the other day. All right, I'm just gonna pause this and then go grab one.
Oh, it's this one.
All right, so I have a coil here. More at the top. When I let go of coils at the top, you should see something go all the way down to the bottom and back. In case you missed it. What you're actually seeing is points where the coils are closer together and points where the coils are a little bit farther apart. So there's some pulse that goes all the way down to the bottom, bounces back. That's a longitudinal wave because the wave moved all the way down and back, but the coils just moved down and back, not all the way. So the wave moved all the way down, but the coils just vibrated up and down just a little bit. So the pulse. So an example here, with battle ropes and longitudinal slinky pulse. So when I'm dealing with a longitudinal wave, it's when one particle or coil or whatever happens to be moves, how much does it influence the next one? Well, I guess that's true for both cases. The longitudinal wave, it's basically you're pushing an object. So sound is another example of longitudinal wave. My vocal cords vibrate back and forth. It compresses air together, which hits other air, which hits other air, which hits other air. The air coming out of my throat is not going to hit your ears for a bit. What you're hearing is the...
Momentarily after you spoke it.
more than momentarily. It depends upon some other factors, but what you're hearing is the molecules that hit your ear, which come from other molecules which hit them, which others that hit them, and others that hit them, all the way, and you trace back this chain of events all the way back to my throat. So one hits another, hits another, hits another, hits another, and eventually that's going to hit your ear. So sound is a longitudinal wave. Now the surface wave, the ideal surface wave,
That's why you can't hear it when you.
is that if you look at the, say you have water here, and you have a wave moving like that, so water. What the particles are doing is actually sort of traveling in a circle. So there is a horizontal and vertical component to it, or I should say parallel and perpendicular component to it. So surface wave is really a combination of transverse and longitudinal. Some textbooks include it as a third type, others do not. I will, for the most part, we're not going to talk about surface waves again. Just wanted to bring it up there and get you on across it. Now, we're about to hit my extension of geology. Or the extent of my geology. Earth. I have seismograph over here, old school seismograph, because that's what I always picture. I have a drum here with, basically this is what's some of my wife's master's degree work. First attempt. We took a barrel with paper on it, you had some sort of smudge pot type thing that blackened the surface of the cylinder. You then attach it to a battery so that the thing would rotate. You have a device with a needle on it, which is basically just scratching the soot off, or whatever the material was, scratching the black off of the barrel. If there's an earthquake, it's gonna shake, and you would see that in print. They're probably far more sophisticated now.
Is light a longitudinal wave?
Light is an electromagnetic wave. Light is,
Right.
falls into the radiation category. If there's an earthquake over here, there are going to be waves, two types of waves being sent. First off, there's what are known as P waves, where P stands for primary or pressure. Primary because they get there first. Pressure waves because it's based upon one object hitting another, hitting another, hitting another. In other words, it's a longitudinal wave.
Earthquakes are longitudinal then?
We'll get there. The other type of wave is the S wave. S stands for secondary,
Or surface?
shear.
Shear wave.
Although you probably could get away with surface to some extent. Secondary or shear. Now a shear, if I have say I've got a piece of material right here, a shear force is one that we have a main axis this way, shear force is perpendicular to that. It causes deformation like this as opposed to deformation like that.
Oh, like you know when you learn about earthquakes, there's like the convergent and then divergent and then the ones that do this.
Yeah, those are the ones I pictured. I guess the other ones where they separate.
So divergent, convergent, and then shear.
Okay.
Is that what you're talking about?
Yeah.
Okay.
Well, I think in the other waves are sent regardless, but I mean we have shear and pressure waves both. But again, we're near the extent of my geology. So the shear waves get there second. Now, if we think about what would cause that, primary waves, I only need is one particle to smack into another, smack into another, smack into another. For sound travels easily enough through gas, it can travel through solids, et cetera, et cetera. Transverse waves, which is this down here. Transverse waves, as a part of the wave moves up, it has to pull on the next one. So it really only travels through medium, transverse waves travel through medium where there's a pulling between particles, which happens nicely in solids. Doesn't happen particularly well in liquids and really horrible in gas.
S waves? Or P waves?
Transverse waves in general. So one of
Is that why tsunamis happen when you have an earthquake in the ocean? Because water doesn't react well?
I would assume that was because of you get a quick displacement of water.
That's part of it, but
Yeah, like again, we're near the end of my geology.
okay.
So P waves get there first. Now, through a whole bunch of math, you eventually get to realize that P waves get there first, partially because, or primarily because, they can go straight through the core. Whereas shear waves cannot. Shear waves have to come around. So it takes longer for them to get there. They're also traveling at different speeds. But with this basic knowledge here, we can start to piece together the fact that the center of the earth cannot be solid.
Oh, no.
And so thus starts the whole idea of there's something that is either gaseous or liquid. Now we think of this plasma in the core, and then we have this crust around the outside. And that is pretty much all the geology I know. My wife was a geology major. She would shake her head hard.
Be glad she taught you anything.
Sorry, missed that?
Be glad she taught you something.
Yeah, she did teach me that. And then the term subparallel, which I have mocked mercilessly. Subparallel means not quite parallel. In other words, not parallel.
Kind of parallel, not enough.
Like 1 degree.
Yeah, I guess it's not
1 degree
that,
off.
it's more like that, or I'm not quite sure where they,
It's like it wants to be parallel, but it's kind of shy.
yeah, there you go. I think that defines it better than I have.
Say it to her.
Or maybe it's finally realized its true self and did not want to be parallel. All right, so we have P waves, S waves. Now, in terms of actually writing this stuff on the board, let me draw.
Can you explain again what shear waves are?
Shear wave is a wave that's going to run through solids so that if I lift up this part of the table here,
Uh-huh.
that causes the next part to be lifted up, causes the next part to be lifted up. We have a primary axis, the way it's going traveling along, its primary axis along that way, but the displacement is perpendicular to that.
Okay. So if pressure is one particle hits another, then shear is
One particle pulls on another, I guess.
pulls on another.
Yeah. So if I'm drawing a transverse wave, I mean, I can just physically, that could describe a transverse wave right there. If I'm doing battle ropes, that would just be a side view of the battle rope. If we're doing a stadium wave, stadium waves are transverse waves. You got one group standing up, the next group then stands up, the next group stands up. So a wave starts traveling through the stadium, but the people, the particles, the medium, are just moving up and down. If I'm drawing a pressure wave, or let's just say sound specifically, the sound wave would, well, I got places where I've got higher pressure, higher concentration of molecules, and then I've got places where there's fewer, and then fewer, and then et cetera. This is not particularly easy to draw, especially if I'm trying to do it quickly. So I have these places where I have high concentration of particles. This is known as compression. In places where I have fewer particles than normal, this is known as rarefaction.
And that's a transverse wave?
No, this is a longitudinal wave.
But they're moving up and down and the motion's going that way.
No, these particles, this is a transverse wave, just a side
Uh-huh.
view. This would be a longitudinal wave, specifically air.
So those aren't a depiction of the same thing?
Well, I'm gonna connect them in a moment.
So
If I
when
were
there's,
drawing sound.
in longitudinal, when there's higher compression, when there's more particles, it's compression, and when there's fewer, that's rarefaction?
Yes.
Okay.
Or in the case of the slinky, if I've got a bunch of coils really close to each other, I've got compression, and then I've got some rarefaction, and then a bunch of close together again. But drawing this is not particularly easy, and so I will tend to draw longitudinal waves like the first example. Just realize that it represents something different. In a transverse wave, this could actually be a physical representation of, this is a physical what I'm looking at, that's what it looks like. If this were representing a longitudinal wave, this peaks represent areas of compression, the troughs represent areas of rarefaction. There's one other way to represent this, which I will do when we get into the Doppler shift. I could also do it sort of from an overhead point of view. Imagine a still pond, I throw a rock into it, and you get that ripple going outwards. The ripple would be where you have the peak. So I could also represent this as just a line at the peaks. This is sort of an overhead view. And in between you have the trough. So with sound, I could represent a sound if I have somebody singing a pure note or I'm playing a pure note. Kind of like that. I could represent it like this, where these represent the points of compression, and in the middle are the rarefaction. So rarefaction, rarefaction, compression, compression, compression.
Well, what about the very center? Is that rarefaction?
The way I have it drawn right now, it would be rarefaction, but it would change. I mean, it's going to oscillate back and forth because these waves are moving outwards.
Interesting.
Questions here?
You said P waves can travel through any state of matter, and S waves can travel through solids?
Yeah. You now need a non-carpeted floor.
Okay.
So we're gonna head out into the hallway. I need a volunteer